So first we'll talk about alpha helices. Okay. In an alpha helix, the peptide backbone is turning in a right-handed fashion such that it forms H bonds with itself between the carbonyl in, if you have amino acid in a position, let's call it I, it's going to make an H bond with the amide group on the amino acid that is I plus 4 positions away. Okay? I will try to count this. Let's look at this one right here. Okay, so this alpha carbon here, here's its carbonyl. And it's making an H bond here, right? Here's the H bond acceptor, here's the H bond donor. So if we count up the helix, this is amino acid I, here's I plus 1, here's I plus 2, here's I plus 3, this is I plus 4, and this is I plus 4's amide. Okay. These are two better links of what I just counted for you that rotate the structure in 3D, show it much nicer, right? Strongly recommended. Two videos that talk about the H bond backbone interactions. Okay, so 2 links. This figure is from the second link. It's well done. I like it a lot. This figure is really poorly drawn. And why is this figure really poorly drawn? Yes. First of all, it's showing the bonds between every 4th, I think, instead of every 5th, like I plus 3. And moreover, it's making it look like the side group, the R group, like the proline is what's participating in the H bond. Right? And it's the backbone. So while I do recommend this link because they actually explain it really well, the cartoons they've drawn are not good. At least not, our book has actually put them where they belong, and I'm happy with it. This is not nice. In terms of how many residues you get per turn, this angle, I haven't decided if I'm going to bother including that right now or later when we do transmembrane. Okay? So you don't need to memorize this yet. If I change my mind, I'll tell you. And again, this pitch and rise, this angstrom order is really all I need, right? Relative order of magnitude, we're on a couple angstroms here. What's up with this arrow? Any guesses on what that arrow is showing? Yes? A dipole. Okay? An overall macro dipole for the entire helix. The entire helix has an overall negative and positively charged end. And it's formed by the summation of a bunch of little dipole moments. Okay? Due to the arrangement of the hydrogen bonds in the alpha helix, the individual dipole moments, okay, and those peptide bonds have directionality to them, give rise to a much larger overall helix dipole. Okay? I have flipped this picture upside down to suit the next picture I show, I think, right? But here we have our oxygen here is going to be negatively charged or more negatively charged than this carbon. The nitrogen here is more negatively charged than this hydrogen. So in both cases, the separation of charge is sort of in the same direction, right? More partial negative here, partial negative up here. So this sort of whole side would be partial negative. This sort of whole side would be partial positive. Here's a picture I've grabbed that sort of shows that. This is our peptide bond here, okay? And it's showing the distribution of charge on the carbonyl, the distribution of charge on this amide, and so the net dipole moment. Again, I don't super care which way you draw the arrow. In this case, it's going from negative to positive. If you draw the arrow the other way, that's fine. Label which side is which for me, that's how I know you know, okay? If you look at the old slide deck, I had this figure turned over. So I flipped it over so that all the arrows pointed down. I didn't flip this one over. I don't know why. But by convention, we have our arrows for the overall macro helix. Most of the resources you look at are going to show, all these little individual dipoles of every single peptide bond pointing from the negative to the positive. So our carboxyl, our C terminus is our negative side, and our amino side is our positive side overall. Okay. Any questions about the helix dipole? Okay. I've cut a set of slides if you have the old deck on microtubules. And tubulin dimers are those proteins anyone's heard of. What are microtubules part of? The cytoskeleton, knees and motors walk along them. Helix dipoles govern the formation of microtubules. These overall macro helix dipoles, the helices will sort of form themselves into these concentric rings of tubulin proteins. I will make a decision pre-Thursday if I have time for that. If not, I will invite you to read those slides on your own. Okay. Maybe an exam question about it. Not specifics, but like, hey, here's a picture of a bunch of helices arranging into a even more macro helix. Like, how come this can happen? Why can this happen? What would be a benefit of this? Stuff like that. Helix propensity. This is definitively on the homework, okay? Amino acids have a different, another word for propensity we might use here is likelihood, okay? Likelihood for being in an alpha helix. And this is the scale from your book, and obviously it's a very relative scale, right? There's no sort of definitive quantifiable values on here. It's a relative scale. Alanine, leucine, methionine, so these are small nonpolar stuff. Typically is what most likely wants to be in a helix, prefers forming an alpha helix, stabilizes alpha helices. If you have a string of a lot of these things in a row, there's a good chance you'll get an alpha helix. Why are glycine and proline all the way at the bottom? They have different reasons for why they're at the bottom. Why is glycine at the bottom? It's too flexible. Doesn't want to stay in a helical structure. Doesn't need to. Much more flex. Much more likely it'll be in some of these unstructured and loop regions. And proline, because it's actually forming a ring with the backbone, it's definitely preventing the ability to form nice alpha helices. And everything else on this list is sort of a relative measure. What other stuff would kind of maybe play in to your propensity for being in an alpha helix? Yes?
Charge.
Charge on the side group. Size of the side group. Shape of the side group. What side groups are nearby, right? What's on either side of you, whether or not you're going to form one of these things, okay? General rules, not perfectly adhered to, okay? There's exceptions to everything. Glycine and proline do appear in alpha helices, okay? I'm not saying just because you have it, it can't. It just tends to be less likely, okay? And like I said, proline is particularly bad simply because it has that ring grabbing onto the nitrogen. I don't particularly know why I put this figure back in here, other than to maybe just remind you, charge could have an effect, size could have an effect, what's adjacent could have an effect, the things that might contribute to helix propensity. Any other questions about that?